Alright, let's do a test review. So let's go over the main equations. We have tangential speed. Our tangential velocity, represented with dt, and is equal to the radius from center of rotation times omega. And omega by itself means radians per second. We have centrifugal force. Centrifugal force equal to mass times tangential speed squared over the radius or distance between to the center of rotation. We have rotational inertia, also called the moment of inertia. Its base formula is equal to mass times distance from center of rotational squared. Note, it depends on how mass is distributed. So here you can see that if all the mass is located at a distance r away, the equation is mass times distance squared. So if the distance is all located r away, this is the base formula. However, if some of the mass is closer, some of the mass is farther away, we have alternative formulas based on how the mass is distributed. But the base equation is simply mass times r squared. We have linear momentum, which is the main topic of this class. We put angular momentum is. The linear momentum is just a product of mass times velocity, which we can turn into angular momentum. Angular momentum is thus equal to the equivalent, so this is linear inertia of mass. The equivalent of linear inertia is rotational inertia. The equivalent of linear velocity is rotational velocity, or angular velocity. So let's look at units. What are the units for inertia? So these are our main equations. What are the units for inertia? Well, we know the main equation for inertia is mass times radius squared. So the units, this is unit notation, the units of inertia, is the units of mass times the units of distance squared. So the units of mass is kilogram, the unit of distance is meters, so the unit for inertia is kilogram times meter squared. What's the units for angular momentum? Well, the units for angular momentum will be the units of inertia times the units of omega. We just solved the units for inertia. It's kilogram times meter squared. And the units for omega is radians per second. However, radians isn't a real unit. And so the units for linear momentum is kilograms times meter squared per second. So, question. Why does ice skater spin faster when they pull their arms closer to their body? Well, we know that linear momentum, or angular momentum, is conserved. It stays constant. So initially, I'll let the arms be represented by having a mass on the outside. So initially, they have some linear momentum. That will be the combination of their inertia times their rotational speed. If an inertia has to deal with mass and the distance between the center of rotation. If the mass is brought in closer, their rotational inertia decreases. But in order for, so if this decreases, in order for L to stay the same, that means that the rotational speed must go up. So this must go up in order for this to stay constant. So by bringing the mass closer to the body, they are decreasing their moment of inertia or rotational inertia, and the rotational speed has to increase to compensate to keep the angular momentum the same. Rotational inertia, or moment of inertia, describes how mass is distributed around a rotational axis. It can also be thought of in terms of Newton's first law of motion, also called the law of inertia. The tendency, or the property, that resist a change in motion, i.e. an object rotating will continue to rotate once an external force is applied on it. An object not rotating will continue to not rotate once an external force is applied to it. The greater your moment of inertia, so the greater the moment of inertia is, the harder it is to so the greater the moment of inertia is, the harder it is to cause the object to stop rotating or start rotating if it wasn't already rotating, or to change its rotation. This means in the absence of friction, so suppose we had a spinning top that is rotating, a spinning top in the absence of friction would spin forever. Going back to the definition of rotational motion is when an object rotates around an internal axis in a continuous way. This differentiates it from orbiting, though we often treat an orbiting object as rotating. Technically, if you want to be semantic in English, you wouldn't say that the moon is rotating around the Earth, you'd say it's orbiting around the Earth. For most purposes, the math, we can assume that it extends all the way to the center. But definition-wise, it needs to be an internal axis for it to be a true rotation. So we have linear equivalents. So linear, we have force, we have velocity, we have mass. This is inertia too. We have acceleration. We have position. So x is really the position. Delta x would be displacement or distance. And the rotational equivalent is torque, omega, the moment of inertia, rotational acceleration, and theta is the position, how much something has rotated. So the rotational equivalent of mass, inertia, rotational equivalent of x is theta. So delta x would become delta theta. We can also analyze these equations. So F equals ma. Torque is also thus I times alpha. So going back, what are the units of omega? Omega should be done, omega units should be in radians per second. That's just the default unit. If you're given cycles per second, so if you're given omega and cycles per second, revolutions per second, then you could just multiply by 2 pi to get you omega in radians. Because there is there is 2 pi radians in one cycle or one revolution. So multiplying it by cycles per second, cycles cancel out and you're left with radians per second. Also remember torque can also be defined as R times the tangential force, where the tangential force, remember, is usually sine theta, depending on how you draw theta. So Newton's laws of motion also apply to rotational laws. Inertia only depends on mass and distance squared. Note though, rotational motion isn't constant, but linear momentum is. Rotational motion usually just describes, I think that rotational motion wouldn't be considered constant. It can be changed if external forces are applied. So do some examples. Let's suppose you have a string ball and it makes 60 revolutions per minute. What would its rotational speed be? By default, rotational speed should be written in radians. So that's 60 revolutions per 1 minute. You multiply by conversion factors. 1 minute is to 60 seconds. So recall that anything divided by itself is 1. 1 minute and 60 seconds are equal, so this is really just 1. And anything multiplied by 1 doesn't change it. So this is our starting value. We're multiplying by 1, so nothing changes. However, the units do get canceled out. There is 1 revolution per 2 pi radians. So this is just 1, because 2 pi and 1 revolution are the same thing. But revolutions cancel out. So 60 revolutions per minute is simply equal to 60 times 1 times 2 pi divided by 1 times 60 times 1. We don't have to include the ones. That's 60 times 2 pi over 60, which cancels out that, which gives us 2 pi, which is equal to 6.283 radians per second. if we wanted to, let's make this 100 millimeters. What would be the tangential speed of this object? So if it was moving at a straight speed, what would be the tangential speed? So tangential speed is equal to radius times omega, where omega is in radians per second. Its distance would be 0.1 meters times 6.283 radians per second, which gives us 0.6283 meters per second. Again, radian is not a true unit, so it disappears. It's radian, again, the reason why radians are so useful is if we imagine a circle, and if we imagine it has a radius of r, and this right here, the arc length, is also r, then theta is a ratio of this length to the radius. So r over r, so let's plug in, let's say this is 1 meter. So 1 meter divided by 1 meter, the meters cancel out. So 1 divided by 1 is 1. But we like adding this unit to it. A meter divided by meter cancels out, but we like calling this something, and we call it a radian. So we have a full circle. Its radius is r. And if we were to go around the whole thing, theta would be 2 pi for the whole thing, whole cycle, radians. We can also see by the definition of a radian why it's 2 pi for the whole thing. So the circumference would be equal to 2 pi r. And a radian is really the ratio of the partial circumference. In this case, for a full circle, would be the full circumference. So the full circumference is 2 pi r divided by, so the ratio of this length, the length around it, to the radius. R's cancel out, and we're left with 2 pi, hence the angle is 2 pi. I think that should be it for the test tomorrow. I'm going to upload the test tomorrow. It will be multiple choice. That should be good as long as you study these notes. Also, go over the PowerPoint. So re-go back over the PowerPoint that was uploaded with another post or with another video. Might re-upload it with this one too. But study these notes and the PowerPoint, and also turn in all your homework.